Assalamualaikum and hello to everyone. In today's video lesson, we will continue with chapter 3 of our syllabus. We will continue with subtopic 3.4 where we will cover the indirect expansion air conditioning system. And as you can see in the subtopic, an example for an indirect expansion system is the centralized air conditioning system. The objective for this subtopic is on the right of the screen. Now, centralized air conditioning systems are large capacity systems usually used in large buildings such as shopping complexes and hospitals. For a centralized air conditioning system, a secondary fluid is used to absorb heat from the conditioned space, thus making it an indirect expansion system. There are several advantages when using a centralized air conditioning system compared to split unit air conditioning systems. Number one, it can solve for crowded condensers as most of the main components are placed inside a plant room. Number two, it provides better indoor air quality because for centralized air conditioning systems, it will involve the mixing of air streams for return and outside air. Number three, it produces less noise because it is not installed at the room directly. And finally, it also saves costs because it can cool an entire building by using a single plant. Now, from the figure given, we can see that there are three major components that makes up a centralized air conditioning system. Number one, the air handling unit. Number two, the chiller unit. And number three, the cooling tower. Now, let's look at the first main component for a centralized air conditioning system called the chiller. A chiller can be considered the heart of a centralized air conditioning system because this is where the refrigeration cycle takes place. The purpose of a chiller is to supply cold water called chill water supply or CHWS to the air handling unit in order to cool the air. Water returning from the air handling unit will be less cold because it has absorbed some of the heat from the air, and this water called chill water return or CHWR. Chillers can either be air cooled or water cooled. For water cooled chillers, it requires a cooling tower connected at the condenser side of the chiller. This figure shows the main components that makes up a chiller plant. The figures on the right and left is that of an air-cooled chiller. As you can see, for an air-cooled chiller, fans are located on top of the chiller at the condenser side. Now, let's look at the second important component for a centralized air conditioning system called the air handler. Air handlers are the component responsible for treating air before it is supplied back to the space. There are two types of air handlers, either an air handling unit or AHU or an fan coil unit FCU. The difference between both air handlers is the type of air conditioning process that it can do and their installation location. Chill water supply from the chiller enters the air handler through water coils, and as supply air passes through these coils, it will result in cold supply air. Chill water, which is now warmer, will return back to the chiller to restore its coldness. The third main component for an centralized air conditioning system is the cooling tower. Cooling towers are only installed for centralized air conditioning system using a water-cooled chiller. Cooling tower will provide a steady flow of cooling water to cool the condenser side of the chiller. Working in a cycle, the cooling water will absorb heat from the refrigerant and will then return to the cooling tower, where it will be then cooled through the evaporation process. The now cool water will be collected at the bottom of the tank, ready to be circulated back to the condenser. Now, during the cooling process in a cooling tower, water inside the cooling tower, there will be some losses in terms of water. The first type of losses is due to evaporation process, where some of the water will evaporate and leave the cooling tower. The second type of losses is due to drift loss. This is due to the suction fan, which pulls the air inside the cooling tower, which eventually carries some of the water out. The third and final type of losses is blowdown losses, which happens during maintenance when cleaning the tank from unwanted contaminants. To make up for these losses, additional water must be supplied to the cooling tower in order to ensure that the amount of water which will be provided to the condenser is enough. This additional water is also called make-up water. During the cooling process, air could enter the cooling tower using two methods, which is either forced flow or natural flow. Forced flow cooling towers require a large fan for suction of air, while natural flow cooling towers uses the buoyancy concept, where cold air will enter from the bottom, and as it absorbs heat from the water, it will start to rise to the top. The direction of air entering the cooling tower can also be different, which can either be cross flow, where the air enters perpendicular to the water stream, or counter flow, where the air enters at the opposite end of the water stream. The figures on top illustrates the types of airflow, either natural or forced, and the figures at the bottom illustrates the direction of airflow, which can either be cross flow or counter flow. Just like any open system, we can also apply the mass and energy balance here at the cooling tower. Please make sure to consider all substances that is entering and leaving the cooling tower during our analysis. Okay, now let's look at some additional information. Although it is not part of the syllabus, I believe that we should at least be aware of the type of air conditioning system that is used in our campus. Now, many might say that our campus uses the centralized air conditioning system. I might say that it is partly correct because I believe that our campus air conditioning system is more akin to the district cooling system. This can be seen in the figure given, where we have a central plant located near our facility building, and from here cold water will be supplied underground to the buildings equipped with the air handling unit. District cooling systems are known for its low cost and energy efficiency. Now, district cooling system performance can also be improved further by incorporating other technological options such as a thermal energy storage or TES. TES acts like a battery where during peak hours it will supply coldness from the ice stored inside the tank to cool the water, reducing the demand for use of the chiller. And during off-peak hours will restore cooling energy by freezing back the water into ice. We have come to the end of this video lesson and also for chapter 3. If there are any questions, please do not forget to leave a comment at the forum section. Thank you for your attention and have a good day.